Welcome to the Deep Dive. Today we're diving deep into, well, a fundamental force of nature, one that shaped landscapes and history: earthquakes.
Absolutely. These events are just such a dramatic display of the power, the change happening right beneath our feet. A constant reminder the Earth is anything but static.
Yeah, definitely keeps you on your toes. Our source material for this deep dive is a pretty comprehensive article from Wikipedia.
Good stuff there.
Right. And our mission, as always, is to take this wealth of information and really unpack it for you. What are earthquakes? Why do they happen? How do we measure their, frankly, immense power?
And their effects, too, which can be so varied and sometimes quite surprising.
Exactly. And maybe most importantly, what can we do to live with them? We're pouring out the key nuggets of knowledge here.
And we'll dig into some fascinating bits like how different faults move, just how much energy these things release. We're talking like atomic bomb levels of energy, thousands of them. And some really unusual quakes, too, some that rupture faster than sound, and others that hide these deadly tsunamis. We'll even touch on how human actions can sometimes play a part.
Okay, lots to get through. Let's unpack this. So, to start right at the beginning, what exactly is an earthquake at its most basic level?
Okay, so fundamentally, it's the shaking of the Earth's surface. Simple as that
A
sounds.
shaking.
But why it shakes? That's the key. It happens because there's a sudden release of energy stored in the Earth's rigid outer shell. That's the lithosphere.
Right.
And this energy travels outwards from the source as seismic waves. That's the shaking you feel.
Got it. And the source mentions other names people use, like quakes, tremors, temblors. They all mean the same basic thing.
Pretty much, yeah. Different words for that shaking. And it also clarifies, which is interesting, that earthquake can technically describe any event that generates these seismic waves. So natural geological shifts, obviously, but also, say, large explosions or other human-caused events.
That's a good distinction. Natural versus human-caused.
Ah.
Okay, so for the natural ones, where does it start? There are specific terms, right? Hypocenter, epicenter.
Exactly. So the hypocenter, sometimes called the focus, that's the actual point deep underground where the rock first ruptures, the very beginning.
Okay, double.
Then the epicenter. That's the point on the Earth's surface directly above the hypocenter. That's the location you usually hear about in the news. You know, the epicenter was 10 miles west of.
Right, the map location. But the real start is the focus, deeper down.
Precisely. And scientists use a couple of terms to talk about earthquake activity in a region. There's seismic activity that's looking at, like, how often quakes happen, what types, how big they are over time.
Kind of the pattern.
Yeah. And then seismicity is a bit more technical. It's the average rate of energy released per unit volume of rock. Helps quantify how active a zone is.
Okay, helps characterize the risk, I guess.
Yeah.
So where does all this energy actually come from? How does it build up and then get released so suddenly? The science behind the shake.
Right. So the main driver for most earthquakes anyway is the rupture of geological faults. These are basically fractures in the Earth's crust where blocks of rock move relative to each other.
Because the tectonic plates are always moving, right?
Exactly. The plates are shifting, but the fault surfaces themselves aren't perfectly smooth. They have these irregularities, bumps, rough patches. The source calls them asperities.
Asperities.
Yeah.
Like sticky spots.
Yeah, that's a good way to think of it. These asperities cause the two sides of the fault to lock together, stopping them from sliding smoothly. But the plates are still trying to move.
So stress builds up.
Precisely. Stress builds up in the rocks around that locked section, storing energy, elastic strain energy. It's like stretching a rubber band further and further. Eventually, that built-up stress becomes stronger than the asperities holding the fault locked. The fault suddenly breaks, slips, and bang, all that stored energy is released in the form of seismic waves.
Oh, okay.
Yeah.
The rubber band snaps. That makes sense. And this whole process, the buildup and sudden release, that has a name, doesn't it?
It does. It's called the elastic rebound theory. Gradual stress accumulation, then sudden rebound or release.
Elastic rebound. Got it. Now, here's something that really jumped out from the source. Only a small fraction of that total energy actually becomes the shaking we feel.
Yeah, it's quite remarkable. The source says something like 10%, maybe even less, of the total energy released actually goes into those seismic waves.
Only 10%. What happens to the rest?
Most of it gets used up breaking the rock itself, creating the fracture surface, or it's converted into heat because of the friction along the fault as it slips.
Wow. So the ground shaking, which can be so destructive, is just a fraction of the total event's power. Amazing. Okay, let's talk more about these fault lines then, where the action is. The source lays out three main types for interplay quakes.
That's right. The main categories are normal faults, reverse faults, which are often called thrust faults, and strike-slip faults.
Okay, let's break those down. Normal faults first. Where do they happen?
Normal faults occur where the Earth's crust is being pulled apart, extended. Think divergent boundaries, like mid-ocean ridges or continental rift zones.
Like in Iceland, maybe?
Exactly. That's a great example. Here, the block of rock above the fault plane slides down relative to the block below it.
And the quakes on these tend to be smaller. The source says less than magnitude 7 generally. Nice that.
It's often limited by how thick the brittle part of the crust is in those areas. Where the crust is stretching and often hotter, like in Iceland, that brittle layer that can actually break might only be, say, 6 kilometers deep. Less rock to rupture means less energy released, generally limiting the max magnitude.
Ah, okay.
Yeah.
Less depth for the break to happen. Makes sense. So what about the second type, reverse or thrust faults?
These are kind of the opposite. They happen where the crust is being squeezed together, compressed, so convergent plate boundaries where plates are colliding.
Right, like mountains being built.
Exactly. In this case, the block above the fault moves up and over the block below it. And when these faults dip at a shallow angle, they're called thrust faults. And these are associated with the most powerful earthquakes on the planet.
The biggest ones.
Yeah. The megathrust earthquakes, we're talking magnitude 8, magnitude 9, even larger. These are responsible for something like 90% of the total seismic energy released globally each year.
90%. Just from this one type of fault setting. That's incredible. So colliding plates, convergent boundaries, that's where the real giants happen.
Definitely.
Okay. And the third type, strike slip.
Strike-slip faults. Here, the two blocks of crust slide horizontally past each other. No significant up or down movement, mostly side to side.
Like the San Andreas fault in California.
That's the classic example everyone knows, yes. Transform plate boundaries are essentially huge strike-slip fault systems. These can also produce major earthquakes, potentially up to around magnitude 8.
Still very powerful, but maybe not quite reaching that megathrust scale typically.
Generally, yeah. The source notes that strike-slip faults often tend to be steeper structures, and the width of the fault zone that can rupture within the brittle crust is maybe more limited, perhaps around 10 kilometers deep. This can constrain the maximum possible rupture area compared to those really wide, shallow-dipping megathrusts, which can rupture over, 50 or 100 kilometers vertically down the dip.
Gotcha. So the geometry limits the potential size compared to megathrusts. And the source also mentions oblique slip.
Right, that's just a combination. Most halts in reality aren't purely normal, reverse, or strike slip. Oblique slip means there's a mix of vertical dip slip movement and horizontal strike slip movement happening on the same fault during the quake.
Makes sense. Reality is usually messier.
Exactly. And one more key point here. It's really only the cooler, brittle parts of the Earth's crust and those subducting slabs diving into the mantle that can store up this elastic energy and then release it suddenly in a rupture.
Right, because hotter rock flows instead of breaks.
Precisely. Once you get down deep enough, typically where temperatures are above about 300 degrees Celsius, the rocks behave more like, extremely thick putty. They deform ductily, they flow, they don't snap catastrophically.
Like trying to break hot taffy versus cold glass?
Yeah.
Good analogy. The source also added a little detail about the stress levels needed for each fault type.
Ah, yeah, that's interesting. Thrust faults, because you're pushing rocks up against gravity and compressing them hard, they generally require the highest levels of stress to make them rupture.
Okay.
Strike-slip faults need sort of intermediate stress levels, and normal faults, where the crust is being pulled apart, actually require the lowest stress levels to initiate slip, because gravity is kind of helping pull the upper block down.
Huh. That relates to the forces involved and maybe how much energy gets released too.
It can influence the stress drop during the quake, which is one factor controlling the energy release, yes.
Right. Speaking of energy, let's really try to grasp the sheer power involved. We use magnitude scales, like the moment magnitude scale today, but it's not intuitive how much energy increases with each step.
No, it's definitely not linear. This is where it gets mind-boggling. Each whole number increase in magnitude represents roughly a 32-fold increase in the energy released.
32 times, not just double or something.
Nope, 32 times. So a magnitude 6 quake releases about 32 times more energy than a magnitude 5. A magnitude 7 releases about 32 times that, meaning it's roughly 1,000 times more energetic than a magnitude 5.
Wow, that exponential jump is just hard to wrap your head around.
It really is, and the source gives that incredible analogy to try and convey it.
The atomic bomb one? Yeah, read that. An M8.6 earthquake releases energy equivalent to, what was it, 10,000 World War II-era atomic bombs?
10,000. That single comparison gives you such a visceral sense of the colossal forces we're talking about deep inside the Earth.
10,000 bombs in one earthquake. Just staggering. So magnitude is linked to the rupture area. How big the patch of fault is that slips and how much it slips, the stress drop. And you mentioned the width of the rupture is often key for the maximum possible magnitude.
Yeah, particularly the down dip width, how far the rupture extends vertically. Those really wide rupture zones, maybe 50 to 100 kilometers or even more, that are possible on the shallow dipping megathrust faults at convergent margins. That's what allows for the truly enormous M9 plus earthquakes, like the ones off Japan in 2011 or Alaska in 1964. A larger area means much more energy released.
Location, location, location.
Yeah.
Not just on the map, but also depth matters, right?
Yeah.
Focus depth. How does the source classify quakes based on how deep they start?
Right, there are three main categories. Shallow focus earthquakes. These start less than 70 kilometers deep.
Okay. Relatively near the surface.
Yeah, and this is where most tectonic earthquakes happen, especially around the active plate boundaries like the Pacific Ring of Fire, that brittle upper crust.
Makes sense. What's next?
Then you have mid-focus or intermediate depth earthquakes. These occur between 70 and 300 kilometers down.
Hitting deeper.
And finally, deep focus earthquakes. These are the really deep ones, starting between 300 and 700 kilometers below the surface.
700 kilometers. Wow. But wait, didn't we just say rock below about 300 degrees Celsius starts to flow instead of break?
Yeah.
How can you get a brittle snap, an earthquake, way down there?
Yes. That's a great question, and it's been a puzzle in seismology for a long time. These deep focus quakes don't just happen anywhere. They occur specifically within those cold, dense oceanic plates that are sinking or subducting back into the mantle.
The Wadati-Benioff zones.
Exactly. So even though the surrounding mantle rock is hot and ductile, the subducting slab itself stays relatively cool and rigid for quite a while as it plunges deeper.
So the slab itself is still brittle enough, even way down there.
Well, it's thought that it remains brittle enough, or perhaps other mechanisms come into play under those extreme pressures and temperatures. One leading hypothesis mentioned in the source involves something called a phase transition.
Phase transition. Like water turning to ice.
Sort of, but with minerals. The idea is that olivine, a common mineral in the mantle, might suddenly transform into a denser crystal structure under the immense pressure deep within the slab. If this change happens rapidly, it could potentially trigger a sudden slip or faulting, causing a deep earthquake.
A mineral changing its structure triggers a quake. That's fascinating. A possible answer to the deep quake mystery. The source also mentions quakes linked to volcanoes.
Yes, definitely. The movement of magma, fluids, and gases beneath a volcano can cause the ground to shake. These are usually shallow tremors and quakes, often occurring in swarms. Sometimes tracking these volcanic earthquakes can help scientists monitor volcanic unrest and potential eruptions.
Right, a warning sign. Okay, let's switch gears slightly and talk about the rupture itself. Once it starts at the focus, how does it spread?
Yeah, so the rupture begins at the focus and then propagates or spreads across the fault surface. You can kind of picture it like a crack spreading through glass, but on a geological scale. It continues spreading until it hits something that stops it. That could be the edge of the stressed area, or a part of the fault that's stronger or perhaps creeping smoothly. Or maybe it reaches the boundary between brittle rock and ductile rock deeper down. For really big quakes, the rupture might even break all the way to the surface.
And the speed of this rupture spread is important too, isn't it? The source mentioned some really unusual speeds.
It is. Normally, the rupture front travels along the fault at a speed that's slower than the shear waves, the S waves, that are generated. But scientists have observed what are called super shear earthquakes.
Super shear. Faster than the S waves.
Exactly. The rupture actually outpaces the shear wave velocity in the surrounding rock. It's like it's breaking the sound barrier for shear waves in a way.
Wow. That sounds incredibly energetic. Does that have specific effects?
It's thought to. The source mentions a potential for a kind of geological sonic boom effect, which could lead to more intense shaking in certain directions. These have been observed in some large strike-slip events, and the source notes that aspects of the devastating 2023 Turkey-Syria earthquakes might have involved super shear rupture.
A geological sonic boom. Incredible. What about the other end of the spectrum? Slow ruptures.
Yes, slow earthquakes. These are ruptures that happen much, much more slowly than typical earthquakes. Instead of lasting seconds, they might unfold over hours, days, or even weeks.
Slow. Does that mean less dangerous?
Not necessarily. There's a particularly dangerous type called a tsunami earthquake.
Tsunami earthquake. Why is that one dangerous if it's slow? That seems counterintuitive.
It's dangerous because it's slow, in a way. The slow rupture can still displace a huge area of the seafloor, generating a massive tsunami. But because the rupture itself is slow, the ground shaking felt on nearby coasts might be relatively weak.
Ah, so people don't get the natural warning sign of strong shaking.
Exactly. They might feel little or nothing, not realize the danger, and then hours later, a devastating tsunami arrives. The source mentions the 1896 Sanriku earthquake off Japan as a tragic example of this weak shaking, but a catastrophic tsunami that killed tens of thousands.
That's a chilling combination.
Oh.
Wow. The source also brings up something about fluid pressure during a quake, co-seismic overpressuring.
Right. This is really interesting. During the incredibly fast slip on the fault, the friction generates immense heat. If there's groundwater trapped in the fault zone, this heat can actually vaporize it almost instantly.
Turning water to steam inside the fault.
Pretty much. This drastically increases the fluid pressure within the rock's pores and fractures. That's the pore pressure. And high pore pressure can effectively lubricate the fault, reducing its strength and influencing how it slips.
The water trapped in the rock actually affects the earthquake rupture itself.
It seems so. And it doesn't necessarily stop there. The source explains that after the main shock, this zone of high fluid pressure can slowly spread outwards through the surrounding rock's fracture network.
And that triggers aftershocks.
It's thought to be a major mechanism for triggering aftershocks, yes. As the high-pressure pulse moves, it can change the stress on nearby patches of the fault system, pushing them towards failure.
And this links back to human-caused quakes too, right? Injecting fluids.
Exactly. This whole concept of changing pore pressure is key to understanding induced seismicity. When humans inject fluids deep underground for things like wastewater disposal from oil and gas operations, or during hydraulic fracturing, or even filling large reservoirs behind dams, they are increasing the pore pressure in the rocks.
And that can unclamp existing faults.
Precisely. It reduces the friction holding faults locked, potentially allowing them to slip and cause earthquakes, even in areas that might not have had significant natural seismicity before. The source explicitly mentions the M5.7 earthquake in Oklahoma in 2011 being linked to wastewater injection.
Yeah, Oklahoma had a huge spike in quakes.
It did, largely attributed to this practice. The source also brings up the potential link, though it says it's not definitively proven, between the massive M8.0 Sichuan earthquake in China in 2008 and the filling of the nearby Zipingpu Dam reservoir a few years earlier, changing the stress and fluid pressure regime.
So our activities, even seemingly unrelated ones like building a dam or disposing of waste, can actually interact with the Earth's stress field and trigger quakes. That's a really important connection.
It absolutely is.
Okay, let's talk about how earthquakes often don't happen in isolation. They come in sequences or clusters.
Very true. Quakes in a particular area are often related in time and space.
The most familiar sequence is probably main shock and aftershocks. What defines an aftershock?
Aftershocks are simply smaller earthquakes that occur in the same general region following a larger earthquake, which we call the main shock.
Why do they happen? Is the main quake finished?
The main shock drastically changes the stress distribution in the surrounding crust. The crust is basically adjusting to this big shift. Aftershocks are the result of smaller readjustments and failures on nearby faults or patches of the main fault that didn't slip initially.
And they're always smaller than the main shock.
By definition, yes. But they can still be large enough to cause significant additional damage, especially to buildings already weakened by the main event, and they can continue for days, weeks, even years after a very large main shock.
And the source clarifies an interesting point. If an earthquake happens that you thought was an aftershock, but it turns out to be bigger than the original one,
then you have to reclassify. The bigger one becomes the new main shock, and the original one is then called a foreshock. It's all relative to the largest event in the sequence.
foreshock, main shock,
Yeah.
aftershock. Got it. What about earthquake swarms? The source mentions Yellowstone as an example.
Swarms are different. They're sequences of many earthquakes occurring in a specific area over a relatively short time, days, weeks, maybe months. But crucially, there's no single main shock that clearly stands out as much larger than the others.
Just a whole bunch of similar-sized quakes clustered together.
Exactly. It's more like a burst of activity without a dominant event. The source gives examples like volcanic areas, such as Yellowstone, where magma movement might be involved, or areas with complex fault networks, like the Imperial Valley in Southern California.
Okay, and then there's this term, earthquake storm. What's that?
That describes something longer term. It's a sequence of large earthquakes migrating along a fault system over years or even decades. Each major quake seems to rupture a segment of the fault, and in doing so, increases the stress on the next segment down the line, making it more likely to rupture next.
Like dominoes falling along the fault.
Kind of like that, yeah. A cascade of stress transfer triggering subsequent large events. The sequence of major earthquakes that ruptured progressively along the North Anatolian Fault in Turkey during the 20th century is often cited as a classic example of an earthquake storm.
Fascinating how these events can link up over such different time scales. Okay, let's talk frequency. How often are these things actually happening?
Well, globally, our instruments are incredibly sensitive now. They detect something like 500,000 earthquakes every year. 500,000.
500,000. That's way more than I would have guessed.
But most of those are tiny, far too small for anyone to feel. Of that 500,000, maybe around 100,000 are actually strong enough to be felt by people locally.
Still a lot. But this ties back to that energy relationship, right? Far more small quakes than big ones.
Exactly. It follows that exponential relationship. For every magnitude 5 quake, there are roughly 10 magnitude 4s, 100 magnitude 3s, and so on. The source gives the UK as an example relatively quiet seismically, but they still feel maybe a magnitude 3.7 to 4.6 quake each year on average, but a more significant M5.6 or larger, maybe only once a century.
And here's a really important point the source makes. If you look at historical records, it seems like the number of earthquakes reported has gone up dramatically in the last century or so. But that's not because more are happening.
Correct. That's almost entirely due to the vast improvement in our detection capabilities. We built a global network of seismometers, especially from the early 1900s onwards, so we started recording many, many more small earthquakes that were always happening but previously went unnoticed.
Better detection, not more quakes. Got it. So what is the long-term average for the bigger ones?
The USGS estimates that, on average, since about 1900, the world experiences about 18 major earthquakes. That's magnitude 7.0 to 7.9 each year. And about one great earthquake magnitude 8.0 or larger per year on average.
18 major and one great quake per year, somewhere on Earth. That average has stayed pretty stable.
Relatively stable, yeah. There might be some longer-term cycles we don't fully understand yet because our detailed instrumental record is only about a century long, but the annual average seems fairly consistent over that time.
And where do most of these happen? Is it evenly spread?
Oh, definitely not. Earthquake activity is highly concentrated along the boundaries of tectonic plates. About 90% of the world's earthquakes, and about 81% of the largest ones, occur in that belt around the Pacific Ocean, the famous Pacific Ring of Fire.
The Ring of Fire, okay.
You also get significant seismicity where continents are colliding, like the Alpine Himalayan belt, and along mid-ocean ridges and other plate boundaries, but the Pacific Rim dominates.
And the source includes a really sobering warning from some scientists about the risk in today's world.
Yes. With massive urban populations now concentrated in some of these high-risk zones, the potential for catastrophic loss of life is immense. Some seismologists have warned that a single major earthquake hitting certain megacities could potentially lead to fatalities numbering in the millions when you consider building collapse, infrastructure failure, and all the cascading effects.
Up to 3 million. That's a terrifying prospect. A stark reminder of why understanding and preparing for these events is so critical. Okay, we've talked about why and where. Let's move to measurement. People often confuse magnitude and intensity. What's the difference?
This is a super important distinction to get right. Magnitude measures the size of the earthquake at its source. It's one number that represents the total energy released. Think of it like the wattage of a light bulb. It's inherent to the bulb itself.
Okay, magnitude, size at source. What about intensity?
Intensity measures the shaking and its effects at a specific location on the ground. It describes what people felt and what damage occurred there. Using the light bulb analogy, intensity is like how bright the light seems where you are standing. It depends on the bulb's wattage, magnitude, but also how far away you are, if there's anything blocking the light, etc.
Ah, okay. So one quake has one magnitude, but it produces many different intensities depending on where you measure it.
Exactly. Intensity will generally be highest near the epicenter and decrease with distance. But it's also strongly affected by local geology. Soft soils can amplify shaking, making the intensity much higher than on nearby bedrock, even at the same distance from the epicenter.
Got it. And we measure magnitude using, well, it used to be the Richter scale, right?
Yeah, the Richter scale was the first widely used one, developed back in the 1930s. It was based on the maximum amplitude of seismic waves recorded on a specific type of seismograph. It worked well for local quakes in California, but it has limitations, especially for very large or distant earthquakes. It sort of saturates.
Saturates, meaning it can't accurately measure the biggest ones.
Pretty much, yeah. So today, the standard is the moment magnitude scale, often abbreviated MARICO.
Moment magnitude, how does that work?
It's based more directly on the physics of the earthquake source. It considers the area of the fault that ruptured, the average amount of slip or displacement on the fault, and the rigidity or stiffness of the rocks involved. It gives a more consistent measure of the total energy released, especially for large earthquakes, and it doesn't saturate like the Richter scale.
And that's the scale where we get that 32 times energy increase per unit we talked about earlier.
That's the one. And for intensity, we use descriptive scales like the modified Mercalli intensity MMI scale. It uses Roman numerals, typically from not felt, up to 12, catastrophic destruction, based on observed effects, what people felt, damage to buildings, ground changes, stuff like that.
Okay, so magnitude from instruments measuring the source, intensity from observing the effects different places. How do we use the seismic waves themselves for measurement and location?
Seismometers record the ground motion caused by different types of seismic waves arriving. As we touched on, there are P waves, primary or compressional waves. They push and pull the rock like sound waves. They travel fastest.
The first ones to arrive.
Right. Then come the S waves, secondary or shear waves. They shake the ground side to side or up and down, perpendicular to the direction they travel. They're slower than P waves.
P, then S.
And finally, you have surface waves, which travel along the Earth's surface like ripples on a pond. They're generally the slowest, but often have the largest amplitudes and cause the most damage, especially far from the epicenter.
So P arrives first, then S, then surface waves. How does that help locate the quake?
Because P waves travel faster than S waves, the time difference between their arrival at a seismic station tells you how far away the earthquake source is. The bigger the gap between the P and S arrival times, the farther away the quake happened.
Ah, like timing thunder after lightning.
Exactly the same principle. If you have arrival time data from at least 3 different seismic stations, you can triangulate to pinpoint the epicenter on the map. And more sophisticated analysis helps determine the depth of the focus, too.
And the source mentioned this technique helped find the Earth's core.
Yeah, pretty cool detail. Back in 1913, Benno Gutenberg used the patterns of P and S wave arrivals specifically, noticing an S wave shadow zone where S waves weren't detected to figure out that the Earth has a liquid outer core because S waves can't travel through liquids, a major discovery based on earthquake waves.
Amazing. And it's worth reiterating. P waves arrive first, but it's usually the S waves and particularly the surface waves that cause the most violent shaking and damage.
Absolutely. Their shearing and rolling motions are what really stress structures.
Once we have all this info, magnitude, location, depth, how is it standardized for reporting so everyone's talking about the same event?
Locations are usually given by latitude and longitude, of course, but they're also often referenced using a system called Flynn-Engdahl regions. It divides the world into 754 geographical zones based on political borders, geography, and seismicity patterns.
Flynn-Engdahl regions.
Okay, so a standard earthquake report will usually include the magnitude, like milliW 7.1, the date and time, usually UTC, the epicenter coordinates, the depth of the focus, the Flynn-Engdahl region name, and often distances to nearby cities or landmarks.
All the key stats. Now, the source mentioned something really cutting edge about detection, using gravity.
Yeah, this blew my mind a bit. Scientists realized relatively recently, around 2016 according to the source, that large earthquakes actually cause tiny, instantaneous changes in the Earth's gravitational field as the rock masses shift.
Instantaneous changes. Faster than the seismic waves travel.
Exactly. Gravity changes propagate at the speed of light, essentially instantly for practical purposes on Earth. Seismic waves travel much slower, maybe kilometers per second, so sensitive instruments could potentially detect the gravitational signal of a very large earthquake before the shaking even starts at distant locations.
Wow.
They actually went back and looked at gravitational data recorded during the massive 2011 Tohoku-oki earthquake off Japan, the Fukushima quake, and confirmed they could see the gravitational signature arriving ahead of the seismic waves at some stations.
Detecting a quake via gravity before the shaking hits. That sounds like it could be revolutionary for early warning systems, especially for the biggest, most dangerous quakes.
It's definitely a really exciting area of research with huge potential implications.
Okay, let's shift to the consequences, the fallout. Earthquakes have such diverse and often devastating effects.
They really do. The most obvious effects are the ground shaking itself, and for large, shallow quakes, ground rupture.
Shaking is what damages most buildings, right?
Yes. The intensity and duration of shaking are key factors in structural damage and collapse. And remember that local site conditions matter hugely here. Soft soils, like in a river valley or an old lake bed, can dramatically amplify the shaking compared to solid rock nearby. That's site amplification.
Making things much worse, even if you're further from the epicenter. And ground rupture.
That's when the fault break actually reaches the surface and visibly displaces the ground. You can see a scarp or offset. For a large earthquake, this offset can be several meters horizontally or vertically.
And if a building or a bridge or pipeline is built right across that fault?
It's going to be sheared apart. Ground rupture is a major hazard for critical infrastructure built directly on active fault traces. There's really no engineering solution for that direct offset other than avoiding building there in the first place.
Right. Another terrifying effect the source talks about is soil liquefaction.
Yes, liquefaction. This happens in certain types of soil, typically loose, water-saturated sandy or silty soils. When strong shaking hits, the water pressure between the soil grains increases rapidly, and the soil temporarily loses all its strength and stiffness. It basically behaves like quicksand.
Like the ground turns to liquid.
Pretty much, and anything built on it can tilt, sink, or just collapse. Foundations lose their support. Underground tanks or pipes might float to the surface. The source mentions the 1964 Alaska earthquake as a famous example where liquefaction caused incredible damage in parts of Anchorage.
Just nightmarish. Of course, the biggest concern is the human impact.
Absolutely. Injuries and fatalities from collapsing structures are the most immediate tragedy. But earthquakes also cause massive disruption by damaging homes, businesses, roads, bridges, power lines, water pipes, communication systems, hospitals, all the critical infrastructure society relies on.
And the source highlights a really important point about who gets hit hardest.
Yes. It emphasizes that the impacts are often disproportionately severe and much longer lasting in underserved communities in developing countries. They may have less resilient infrastructure to begin with, fewer resources for emergency response and rebuilding, and recovery can take far, far longer. Vulnerability isn't just about geology, it's deeply tied to socioeconomic factors.
That's a crucial point. Hazard plus vulnerability equals disaster risk.
Exactly. And the aftermath brings a whole host of secondary problems. Potential outbreaks of disease due to contaminated water or lack of sanitation, shortages of food, clean water, shelter, and the psychological toll, anxiety, depression, PTSD among survivors can be profound and long-lasting.
Recovery is a massive challenge. The source lists some truly devastating historical quakes.
It does. The 1556 Shaanxi earthquake in China estimated over 830,000 deaths, including from the aftermath like famine and disease. The 1976 Tangshan quake, also in China, the deadliest of the 20th century. And the 1755 Lisbon earthquake in Portugal, around 60,000 killed, not just by the quake, but also the massive tsunami and fires that followed. Just staggering tolls.
Really puts the potential scale of devastation in perspective. Landslides are another major killer triggered by quakes.
Yes, strong shaking is incredibly effective at triggering landslides, especially in mountainous regions. The source mentioned a study looking at landslide fatalities. China had the highest number, largely due to the thousands triggered by the 2008 Sichuan quake. But Peru, Pakistan, other places also see major landslide impacts. Interestingly, that study noted strike-slip faults seemed particularly prone to triggering deadly landslides.
And fires. Notoriously hard to fight after a big quake.
Very much so. You get broken gas lines igniting, downed electrical wires sparking, and at the same time, the shaking often breaks water mains, so firefighters lose their water pressure. It's a terrible combination. The huge fire that swept through San Francisco after the 1906 earthquake actually caused more destruction and likely more deaths than the initial shaking itself.
Wow. And then there's the threat from the ocean. Tsunamis.
Tsunamis. Giant waves, usually caused by large undersea earthquakes that suddenly push up or drop down a huge section of the seafloor, displacing the water above it. Big submarine landslides can also trigger them.
And they travel incredibly fast across the ocean.
Incredibly fast. The source says 600 to 800 kilometers per hour in the deep ocean. That's like jetliner speed. They have very long wavelength, so they might only be a meter or so high in deep water, passing unnoticed under ships. But as they reach shallow coastal waters, they slow down, pile up, and can surge inland as devastating walls of water, sometimes tens of meters high.
And they can travel across entire oceans.
Yes, a tsunami generated off the coast of Chile can cause damage hours later in Hawaii or Japan. The 2004 Indian Ocean tsunami is the horrific modern example everyone remembers, triggered by that massive M9+ quake off Sumatra, affecting countries all around the ocean basin.
It's devastating. The source mentions a rough magnitude threshold for tsunamis.
Yeah, it notes that destructive tsunamis are usually generated by quakes of M7.5 or larger, especially shallow ones involving vertical movement of the seabed. But there are exceptions, like those slower tsunami earthquakes we talked about earlier.
Right. And flooding can happen in other ways, too, as a secondary effect.
Yes. If an earthquake damages a dam, it could lead to catastrophic downstream flooding. Or, if a quake triggers a massive landslide that blocks a river, it can create a temporary landslide dam. These natural dams are often unstable and can fail suddenly, releasing the impounded water in a huge flood.
The source mentioned a specific risk in Tajikistan.
Yes, the Usoy Dam. It was formed by a huge earthquake-triggered landslide in 1911. It holds back the enormous Saras Lake. There are ongoing concerns about the stability of this natural dam, and its potential failure could, according to the source, affect something like 5 million people living downstream in several countries. A ticking time bomb, potentially.
Goodness. Shows how these hazards can be linked. Okay, given all these devastating potential effects, what can we actually do about earthquakes? How do we manage the risk?
Well, the first thing to understand, and the source is very clear on this, is the difference between earthquake prediction and earthquake forecasting. They sound similar, but they're crucially different.
Okay, prediction versus forecasting. Let's unpack that. What's prediction?
Earthquake prediction, in the scientific sense, means specifying beforehand the location, time, and magnitude of a future earthquake within fairly narrow limits. Like saying there will be a magnitude 7 quake on this specific fault segment in the next 6 months.
Right. The Holy Grail, everyone wishes we could do that.
Exactly. But the source states very clearly, despite decades of research and effort, scientifically reliable, reproducible earthquake prediction of this kind is not currently possible. No method has ever consistently worked.
So anyone claiming they can predict the next big one, we should be skeptical.
Highly skeptical. There's no scientific basis for it. The source also specifically debunks myths like earthquake weather. There's no link between weather patterns and earthquakes.
Okay, so prediction is out, for now at least. What about forecasting? How is that different?
Forecasting is different. It's a probabilistic assessment. It's about estimating the likelihood of seismic activity in a general area over much longer timescales, years, decades, even centuries.
More like a long-term weather forecast than predicting tomorrow's rain exactly.
That's a good analogy. For well-studied fault systems, scientists can look at the history of past earthquakes, the rate at which strain is building up, and make probabilistic statements like, there is a 60% probability of a magnitude 6.7 or larger earthquake occurring on this fault system in the next 30 years. It's about understanding the long-term hazard level, not pinpointing the next event.
That makes sense. Understanding the odds helps us prepare, even if we don't know the exact timing.
Precisely. It informs building codes, land use planning, insurance rates, preparedness efforts.
What about earthquake warning systems? They exist, right? How do they fit in?
Yes, earthquake early warning EOW systems are different again. They don't predict quakes before they happen. They detect an earthquake just as it begins, very close to the epicenter, using the arrival of the first fastest P waves.
Ah, they detect the start of the shaking near the source.
Right. And they instantly send out alerts electronically faster than the slower, more damaging S waves and surface waves are traveling outwards. This can give people and automated systems located further away precious seconds, maybe even tens of seconds or a minute, depending on distance, of warning before the strong shaking arrives.
So not prediction, but rapid detection and warning during the event itself. What can people do with that warning?
It's enough time to take protective action, drop, cover, and hold on, to slow down trains, stop elevators at the nearest floor, shut off gas lines, allow surgeons to pause procedures. Those few seconds can save lives and reduce damage.
Definitely valuable. Beyond warnings, what are the main strategies for preparedness that the source mentions?
There's a whole range. A big one is earthquake engineering, designing and constructing new buildings, bridges, and other infrastructure to be resistant to seismic shaking following modern building codes.
Building things stronger in the first place? What about older buildings?
That's where seismic retrofitting comes in. Modifying and strengthening existing, older structures that weren't built to current standards to make them safer. This can be expensive, but is crucial for reducing risk in areas with lots of older building stock.
Engineering solutions? What else?
Earthquake insurance is a financial tool to help homeowners and businesses recover after damage. Emergency management planning by governments and organizations is critical, having plans for response, rescue, shelter, medical care.
And on an individual level, what can people do themselves?
The source lists several practical steps. Secure heavy furniture, water heaters, bookshelves that could fall and injure someone. Know where your gas and water shutoff valves are and how to use them. Have an emergency kit with water, food, first aid supplies. And crucially, practice what to do during shaking. Drop, cover, and hold on. Get under a sturdy table or desk. Protect your head and neck.
Simple actions that can make a big difference.
Absolutely. And for people in coastal areas, tsunami preparedness is vital too, knowing the evacuation routes, understanding natural warning signs like strong ground shaking or the sea suddenly receding.
And the source even mentions artificial intelligence playing a role.
Yes, it gives the example of the Igor Expert system. It's apparently part of a mobile lab that uses AI to quickly assess the seismic vulnerability of existing masonry buildings, which are often very dangerous in quakes. It helps engineers plan effective retrofitting strategies, especially for historic city centers like Lisbon or Naples, where it's been used.
Using AI to make older cities safer.
Oh, that's a fascinating application. Okay, just briefly, before we wrap up, how have earthquakes been viewed in human culture historically?
Well, before science gave us the plate tectonic explanation, people came up with all sorts of ideas. The source mentions early Greek philosophers thinking earthquakes were caused by winds trapped underground, or subterranean thunderstorms, or tension between the elements of earth and water.
Trying to make sense of such powerful events. And mythology often had specific figures responsible. Oh yes, lots of cultures had mythological explanations. The source lists Loki from Norse mythology being punished underground. The Greek sea god Poseidon was also the earth shaker. There's the giant catfish Namazu thrashing around under Japan, a giant earth buffalo called Togu in Taiwanese folklore. Powerful beings causing the tremors.
Interesting how widespread those kinds of stories are. Even religious texts mention them.
Yes, the source notes that earthquakes are mentioned in the New Testament Gospels, for instance, often accompanying significant events.
And how about modern popular culture? How are quakes usually portrayed now?
Often movies and books focus on the disaster itself and the immediate chaotic aftermath, reflecting maybe the collective memory of infamous events like the San Francisco quake or Kobe in Japan. And the source points out a particularly popular fictional theme, especially in the U.S., the anticipation and imagined devastation of the big one hitting California along the San Andreas Fault.
Yeah, that's definitely a recurring trope. Finally, the source reminds us that this isn't just an Earth thing.
Right. Seismic activity happens elsewhere, too. We've detected Marsquakes on Mars with NASA's InSight lander, giving us clues about the interior of Mars. The Apollo astronauts left seismometers on the moon that detected moonquakes, likely caused by tidal stresses and cooling of the lunar interior. So the phenomenon of planetary bodies shaking isn't unique to us.
Marsquakes and moonquakes. Fascinating. Well, that brings us towards the end of this deep dive into earthquakes, drawing heavily on that comprehensive Wikipedia source.
We've covered a lot of ground, haven't we?
We really have. From the basic definition shaking, and the science behind it, the elastic rebound theory.
To the different types of faults, normal, reverse thrust, strike slip, and that mind-blowing energy release, especially from megathrusts.
Right, and how we measure the magnitude versus intensity, P waves, S waves.
Yeah.
Even using gravity now, potentially.
Then all the diverse effects, shaking, rupture, liquefaction, landslides, fires, tsunamis, the immense human impacts, especially on vulnerable communities.
And finally, how we try to manage the risk, the crucial difference between prediction, which we can't do reliably, and forecasting, which we can, probabilistically. Plus, preparedness, engineering, early warning.
It's such a complex topic, linking deep Earth processes with surface hazards and human society. Hopefully, this discussion is giving you, our listener, a clearer picture and some valuable takeaways.
Absolutely. And as we finish, here's a final thought for you to perhaps mull over. Think about that stark difference between prediction and forecasting. Knowing we can't predict the exact time and place, but we can assess long-term hazard. What does that really mean for how you think about preparedness, either personally or for your community?
Or maybe reflect on those surprising ways human activities like fluid injection or reservoirs can actually interact with these powerful geological forces.
Or just contemplate, again, that incredible scale of energy involved. that M8.6 quake being like 10,000 atomic bombs.
Yeah.
What aspect of this deep dive stands out most to you? Something to think about.
Powerful forces indeed. Important questions to consider.
Thanks so much for joining us for this deep dive.